Okay, so let's pick up where we left off. We had talked about the applyAllItter method, and if you recall, that one had just gone through a loop just saying, doing computes on all the tasks that were created in a loop, and it relied on work stealing in order to disseminate the different tasks to the different threads in the worker thread pool. So now we're going to take a look at a different implementation. This is called applyAllSplit, and it's going to use a different mechanism in order to be able to distribute the tasks to the worker threads. And we'll see that there's some pros and cons with this approach. So once again, the purpose of this method is identical to before. It's going to apply some kind of op function to every element in a list using the fork join pool that's passed in as a parameter. Except this time it's going to do it by recursively splitting things up. And there's a nested class called SplitterTask, which extends recursive task, and it's going to recursively partition the list evenly and efficiently, and it'll run each of the half of the partitioned list in a fork join task. And it's going to keep doing this until it splits it up into atomic-sized chunks. So this is kind of classic divide and conquer style use of fork join. So this is the sort of the canonical example of how to use the fork join framework. And you'll see a lot of things in fork join framework look like this. This is a little bit, as we'll see, more complicated than the other approach that used the iterative method of just throwing things into the fork join pool, but it'll be somewhat more complicated to program. What we do first is we create a new splitter task, one of these guys, passing in the entire list, and then we invoke that in the fork join pool. Remember that invoke is a two-way method, so that will start things running, and then it'll get the result back. It'll block, waiting for the result to be done. Let's take a look at the splitter task. We'll take a look at this in a couple of different pieces. So this implementation of splitter task is going to recursively split the list evenly in half, and then it'll also do some data copying. You see, that's kind of the downside with this approach, but it's very canonical, as I said before. Each instance of SplitterTask is going to have a list field, and the constructor will simply take a reference to the original list, and it'll stash it away here in this field. And what's going to happen is, as we split this thing up recursively, this will be pointing to different parts of the list over time, different copies of the list over time. Here's the compute method. Remember, compute is the workhorse method for a recursive task, so SplitterTask is a recursive task. And I should also point out at the very beginning, the first call to SplitterTask, the one right here, gives the whole list. So we start with the whole list being considered. So that gets stashed away. Here's the compute method. You can see this is the workhorse. This does all the processing, but it'll do it in a very cool way, as we'll see in a second. The first thing that this SplitterTask's compute method does is it has the base case for the recursion. I'm sure you all remember recursion, where you have a base case where you check to see if you're done, and then otherwise you have a recursive case where you split things up and work on different parts. So what we're going to do here is we're going to check to see if the size of the list that we have at the moment is less than or equal to 1. So let's assume, for sake of argument, it has one element in it. So when it has one element in it, we're basically done. So what we're going to do, or not done, we're basically at the base of the recursion. So we make ourselves a new result list, which is initially empty, as you can see here. And then we iterate through the list that we have that was initialized by the constructor here. And we go through that list, which has one item in it. And we go ahead and we add the result of applying the operation on the element in the list, in the element in the original list, which is T here. We apply the operation, and then we add that to the result list. So as a result of doing this loop, it should typically run one time. And then we return the result list. So this result list that's returned here applied the operation to the single element in it. So that's the basis case for the recursion. Otherwise, we don't have an element that's atomically sized. It's bigger than 1. could be 2, it could be 4, it could be 3, it could be 100, whatever it is. What we're going to do is we're going to go ahead and determine the midpoint of that list. So we take the current size of the list and we divide it by 2. So that's a really easy way of dividing a list in half, much like your array list splitterator stuff that we've talked about before, and your array splitter, your unsynchronized array splitter that you worked on before. So we divide things in half, and then we're going to do one thing on the first half of the list and something else in the second half of the list. So let's go ahead and take a look and see how this is going to work. So the first thing we're going to do is we're going to create a new task. So LT, L stands for left, so left task, LT, is going to be set equal to a new splitter task, which is going to be a sublist of the original list from 0 up to the midpoint. So we're going to basically take the first half of the list, the left-hand side. We're going to make a sub-half of that list. We're going to make a splitter task, so that'll get a sub-half of the list. And then we take that splitter task, we create the new splitter task, and we fork it, and we store it in this new LT fork join task, which is a fork join task to a list of T. So what this is going to do, and we'll see this in more detail when we visualize this shortly, this is going to end up recursively decomposing the overall list up into subtasks, and then it's going to have those subtasks go off and work in parallel using worker threads in the fork join pool. So remember what fork does, when we fork it, that arranges to place this thing into the current thread's deck, the current worker thread's deck. And then, of course, it'll most likely be stolen by some other thread. So that the left-hand side is sublisted, subset, if you will, and forked, which puts it on the deck to be processed by some thread in the pool. Then what we do is we update mList, which is the current list in this fork join task object, this splitter task. The right-hand side, we go ahead and we create mList to be a sublist from mid to the end of the list. So this is the right-hand side of the list. So this guy up here handles the left-hand side of the list. This guy right here handles the right-hand side of the list. And then we go ahead and we call the compute method recursively, right? We're in compute already. And now we're going to update the list. So we have half the list. And now we call compute on this object, which is now the right half of the list. And that will go ahead and recursively call this thing. And of course, that recursion will continue until we reach back to the basis case where there's a list of only one element in it. And of course, we know that'll happen because each time we're dividing the list in half. So after log n divisions in half, we'll eventually end up with a list that only has one element in it. So compute, notice here, compute is called in the same task as the parent, in other words, the original compute method from the original splitter task, and that's to minimize context switching. So we're going to fork off the left-hand side, but we're going to use the current thread to process the right-hand side. So compute goes off, it does its thing, and of course compute will block, but this fork will not block. That fork has been put into the deck, which will most likely be stolen by another thread, and it'll run in parallel. So after compute finishes, we've processed the right-hand side of this sublist, and then we're going to go ahead and join with the results. So when we say LT join, that will go ahead and get a list back, which is the left-hand side results from LT. So notice how compute gives us the right-hand side results, and then when that's finished, we go and we join with the left-hand side. And hopefully, while we've been sitting here happily computing away, this left-hand side has been taken off the deck by some other thread in the worker pool, has been stolen, and it's going to go ahead and process that thing. So hopefully by the time we get done with compute here, the left-hand side will be done, and so left-hand lt.join will return quickly. And notice that compute must be called before join. We can't be joining before we finish computing, otherwise it wouldn't make any sense. We wouldn't get any parallelism happening here. So of course, this call might block if for some reason the left-hand side isn't actually done processing that could block. But it may be done by that point, and probably will be if it's balanced well. So at that point, what we're going to do is we're going to take the right result, the result of the right-hand side processing, and we're going to add it to the list on the left-hand side result. So left result dot add all right result, that will combine everything together. So now we've got a complete set of results for whatever the mList was originally when we came into this particular compute method. And then we return left result, which has got right result appended to it. And the key thing to note here is that because left result and right result are array lists, there might be data copying going on here. If the array list isn't big enough, it has to make a copy. Yes, Gavin? Good question. So the question here is, when does this start to run? So remember when you create this new splitter task, which has the left-hand side of the list, and you fork it, what happens? Remember, fork arranges to execute the task at some point in the future. What does it do? It sticks it on the deck of the current thread. Well, remember, the current worker thread is about to go off and do compute. So that thread will be busy for however long it takes compute to recursively decompose and do its thing. So chances are the left task that's on that worker thread's deck will be stolen by some other thread. And if that other worker thread steals that particular left task from the front of the deck or the tail of the deck, well, the end of the deck, let's say the end of the deck, then those things will in fact run in parallel. Now, there's obviously some non-determinism going on here because stealing doesn't happen instantaneously, but in steady state, especially if you have a very large list and you have recursively decomposed all these things and have lots of decks with lots of things on them, stealing will start to happen and this thing will run in a fairly balanced and parallel way. So this is a very canonical way of using the fork join pool. And the key things to note here is we fork, which will arrange to run this. We then start computing in the same thread that initiated the fork. Chances are someone will steal that LT from the deck of the current thread because it's doing something else, it's doing compute, such that when we get done with the compute in the current thread and go to join, chances are the left task will probably be close to being done. Okay, so I think you'll agree that this implementation, while super cool, is harder to program and harder to understand because it's recursive. Whereas the original approach we talked about last time, the one that was with the applyAllIter implementation, it just went through the list, throwing things into the current thread's deck. So it threw everything into the current thread's deck, and then the other threads would come and steal from it. Whereas this approach is recursive, so it's going to be more efficient, but it's harder to program and a bit harder to understand. So to help make things a little easier to understand, let's visualize what's going on here. This will give you, hopefully, a more right-brain view of what's happening rather than trying to look at code alone. Code is obviously important, but sometimes it helps to get a bigger picture view. So here's where we start. When we say fjpool invoke new splitter task list, that is creating a single initial task, task 1, with the entire list, and it's inserting that into the shared queue of the fork join pool. And in this particular case, notice that the invoke method, as we've talked about before, allows a non-fork join task client, which is basically this thing. This is not running in the fork join pool yet. It's invoking the invoke method in the fork join pool, but it's not part of the fork join pool yet. It goes ahead and inserts this task into the internal shared queue that all fork join pool instances have. So again, new splitter task, it's the first one, it's say task 1, and it's got a list to the entire input we're trying to process, which let's say it has lots of elements in it. So here's what happens henceforth. One of the threads in the pool, one of the threads, worker threads in the fork join pool, will go ahead and pull that task 1 out of the shared queue. And then the recursive decomposition will start to happen. And so as you can see here, things will get split up into these subtasks. So we'll start with, task 1 will be split up into subtasks, and those things will end up being distributed across the different threads in the pool. And because of the way the recursive decomposition works, because each new thread in the pool that steals work from someone else's task, remember it'll steal a big thing to work on, a big sublist, then that thread will start to recursively decompose that thing, and that'll create more subtasks, and those things in turn will be split across all the other worker threads in the pool. So what you'll end up with is a nice balanced sort of tree, if you will, of subtasks that are all running in different threads in the pool. Whereas with the applyAllItter implementation, we threw everything into the original worker threads deck, and then those would be stolen by all the other threads. In this approach, we decompose stuff, and so we have a better, more even split. So the consequence of this is work stealing overhead is lower because we don't have to steal as much work. We steal very little work because things are recursively being decomposed. However, copying overhead is a lot higher because now we have to copy all these sublists, we have to split them, then we have to copy them back by doing the add all method, which might allocate memory, and we have to copy everything, and there's just extra method calls. So this has higher method call overhead, higher copying overhead, but less work stealing overhead. And we'll see shortly what the consequence of less work stealing overhead is. The forked subtasks and compute subtasks will typically end up running in parallel, again, because of the way that we're decomposing these things. And as before, compute runs in the same task as its parent in order to optimize its performance. So we don't end up, you could fork again, but that would be pointless. So there's a balanced tree of join calls, which scales better than the applyItter method, where we had one thread that had to join everything from all the other threads. So this will take less time, it'll have less overhead. And keep in mind that in this particular approach, join actually returns a value because, after all, SplitterTask is a recursive task, which means that compute returns a value, which in this case is a list of t. Okay, so that's the end of the applyAllSplit method. So the good thing, lower work stealing because we do recursive decomposition. The downside is extra data copying and more method calls. And we'll see very soon what the pros and cons of this are empirically.